All right, welcome to how to write net ionic equations. And so in the problem that we're given, it says write the net ionic equation for the precipitation reaction that occurs when aqueous solutions of silver nitrate and potassium phosphate are mixed. So the first thing that we have to do, step one, is determine the type of reaction. Is it a combination, a combustion, decomposition, precipitation, neutralization, or redox reaction? And because it says that we have a precipitation reaction, we know that it's going to be a precipitation. The next step is to start to predict the products and determine their physical states. So first, we know that this reaction has silver nitrate, which is aqueous because it tells us, and that's going to be reacting with potassium phosphate, which is also going to be aqueous. And now we can predict the products of this reaction. And so what we know is that we're going to use, in a precipitation or double displacement exchange or metathesis reaction, we're just combining the outside versus the inside and combining those to make new products. And so the Ag ion, silver ion, Ag+, and the phosphate anion, PO4 3-, are going to combine to give us Ag3, PO4. And when we look at the solubility rules, the silver phosphate, is going to be insoluble and it's going to precipitate out. In every precipitation reaction, we have something precipitate out, something that's going to be insoluble. And lastly, we have our other product, which is going to be potassium nitrate coming from the potassium ion and the nitrate anion. This is going to be aqueous because it is soluble. So that is step 2. Step 3, we need to balance the molecular equation, which means that we actually need a 3 in front of the silver nitrate and a 3 in front of the potassium nitrate. We now have a balanced molecular equation, and we can go on to write the ionic equation. For the ionic equation, we're then going to ionize anything that is aqueous, that is a strong electrolyte. So the silver ions are going to ionize because silver nitrate is aqueous, it's an ionic compound, thus it's a strong electrolyte. And so the silver ions, Ag+, which we have 3 of them based on what's in front here, and we also have 1 nitrate anion, but we had 3 of those based on that 3 in front again. Now both of these are going to still be aqueous. We're then going to react that with the potassium ions, which, because we have a 3 here in front, tells us that or 3 as a subscript, tells us that we have 3 potassium ions for every 1 phosphate anion. These are a strong electrolyte since it is an ionic compound, and so we have 3 K+ ions plus a phosphate anion, which is also aqueous. And then on the other side, we have silver phosphate, okay? And because silver phosphate is insoluble and it's written as a solid, it is not going to ionize. So we just continue to write it as Ag3PO4 as a solid plus our potassium nitrate. It says we have 3 potassium nitrate. It is an ionic compound, thus it is a strong electrolyte and is going to ionize completely. We end up with 3 potassium ions plus we have 3 nitrate anions, which are also aqueous. So that brings us to step number 6, which means we can eliminate the spectator ions and reveal the net ionic equation. We have 3 nitrate anions on this side, 3 nitrate ions on this side. We have 3 potassium ions on the reactant side, 3 potassium ions on the product side. And now we can write what's left for our net ionic equation. And in that reaction, we end up with 3 silver ions, which are aqueous, plus we have a phosphate anion, which is also aqueous, and that's going to produce our insoluble precipitate, which is silver phosphate as a solid. This completes our net ionic equation for this reaction. So step 1, determine the type of reaction. Step 2, predict the products and determine the physical states. Step 3, we balance the molecular equation. Step 4, we determined if the reactants or the products are strong electrolytes, weak electrolytes, or non-electrolytes. Step 5, we wrote the ionic equation. And then step 6, we eliminated the spectator ions to reveal the net ionic equation.